Okay guys, in this video we are going to be talking about free energy. The idea of this section builds upon the second law of thermodynamics, where one must consider the entropy change of both the system and the entropy change of the surroundings in order to judge whether or not a process will be spontaneous. The purpose of this section, concentrating on the system, the main idea here is that under certain conditions, you can focus exclusively on system quantities to judge spontaneity. So that's why it's entitled Concentrating on the System. Okay? So the Helmholtz free energy has this formal definition here. The Helmholtz energy A is the internal energy of the system minus the product of temperature times entropy. It's an extensive state function, and it will have units of joules or kilojoules. The Helmholtz free energy serves as a criterion for spontaneity under conditions of constant temperature and volume. To explain what's going on here in this first set of equations, please recall that the Clausius inequality given here is consistent with the second law of thermodynamics. Okay, so this is true for any spontaneous process, and the equality is true for a reversible process. So this is a criterion for a spontaneous, irreversible process, and what's being written here in the equation, this portion here plus this inequality here, this is just the Clausius inequality. And then what's going on is we're rewriting the terms. For example, under constant volume conditions, the infinitesimal heat is just the infinitesimal change in the internal energy. Furthermore, if you assume that temperature is constant, you can essentially factor out the differential operator and write this expression here as D as the differential of the quantity U minus Ts, which is the definition of the Helmholtz energy. So what we've shown here is that for conditions of constant temperature and volume, the criterion that the Helmholtz energy decrease is a substitute for the second law. Okay, and so that's why I say that this is a criterion for spontaneity under conditions of constant temperature and volume. The nice thing about this is that A is a system property. It doesn't explicitly depend upon the surroundings. It does implicitly, but you can calculate it using system-only quantities. For finite changes at constant temperature and volume, we have this version of the spontaneity criteria: delta A equals delta U minus T delta S. You know, we've learned how to calculate delta U and how to calculate delta S for a process, and so it's relatively easy for us then to put together what delta A is. And the criterion for spontaneity is that the change in the Helmholtz energy must be less than or equal to 0, where the equality corresponds to a system that is at equilibrium. Here we're being asked to perform a sign analysis of delta A, and so this is a very useful exercise. So I'm going to write out the terms, and then what we're going to do is run through some different scenarios. So let's first consider the scenario where the internal energy of the system decreases. Okay. We've got the minus sign here in the equation. Temperature is always positive. And then let's consider the case where the entropy of the system increases. And then we'll ask ourselves, what would be the sign of delta A under these conditions? Well, you got something that's negative minus something that's positive. So in this case, delta A will always be negative, regardless of the temperature. And so a process that satisfies these two conditions negative delta U and positive delta S will always be spontaneous, at least under conditions of constant temperature and volume. Let's run through another scenario. How about the case where delta U is positive, so this would be an endothermic process, minus temperature, and let's let the entropy be negative. Well, in this case, we've got a positive sign minus a negative sign, and so this is going to always be positive, regardless of what the temperature is. And so this process will never be spontaneous, because delta A is positive. Right? Remember, our criterion for spontaneity is that delta A is less than 0. There's a couple of mixed cases. Let's run through the case where, well, let's go ahead and do delta U negative. But instead of creating entropy, let's let the process consume entropy. No, I should have made that negative. That didn't help much. All right, so we've got here, I'm just going to scratch that out. So negative minus temperature, and then the entropy decreases. Well, for this situation here, the energy term tends to make the process spontaneous because that contributes to a negative sign for delta A. However, because the entropy is negative and we've got this minus sign out in front, this is going to be positive. So this is going to tend to make the process non-spontaneous. So we have a competition between energy and entropy. And which one is going to win is going to depend upon the value of T. Okay, so I'm going to write, when temperature is small, that means that this term will be negligible compared to the energy term. And so it's negative at low T, and then it's positive at high T. Okay, and so for the case where the temperature is low, delta A is negative, that means the process will be spontaneous at low temperatures. And since it's positive at high temperatures, it'll be non-spontaneous at high temperatures. So we have sometimes spontaneous. So I'll say spontaneous at low T. There's another case where we have an endothermic process, but entropy is created in the system. Here now, the two terms are still competing, but they're competing in the opposite way. This time, entropy tends to favor the spontaneity of the process because of the minus sign out in front, whereas the energy term tends to make the process non-spontaneous. So we have the opposite sort of conclusions. It's going to be positive at low T and negative at high T, which means that it's spontaneous only at high temperatures. This is something that you want to be able to do, this type of analysis, for both delta A, and later we're going to discuss delta G. And the sign analysis works in the same way for both of them. Okay, so this is something that you want to be able to do on your own and be able to think through when you're dealing with problems. The Helmholtz energy has another important interpretation beyond just spontaneity. The Helmholtz energy represents the non-thermal energy portion of the internal energy that is available to do work under conditions of constant temperature. And so here what I'm showing, this is just the first law rearranged. And then using that, using the Clausius inequality, you can replace dq with this and with minus TdS, and then it becomes an inequality. And for conditions of constant temperature, you can factor out the differential, and what you see is that the infinitesimal work is always greater than or equal to the infinitesimal Helmholtz energy change. The way to interpret this result, the way I interpret it is I like to think of the free energy as not simultaneously, as either a maximum or a minimum amount of work. And for the case where the process is spontaneous, that is when the Helmholtz energy is negative, the Helmholtz energy represents the maximum amount of work that you can derive from the system. So for a spontaneous process, this is one, for example, a chemical reaction. You're trying to use a chemical reaction to drive a motor, to drive an electric motor or something, or just to perform some type of work. The Helmholtz energy represents, when it's negative, it represents the maximum amount of work that can be derived from that process under conditions of constant temperature. Simultaneously, or under different conditions where you're considering a non-spontaneous process, so in that case, the Helmholtz energy would be positive. The change in the Helmholtz energy would be positive. Under those conditions, the Helmholtz energy represents the minimum amount of work that's required in order to make the process occur. Right? So for a non-spontaneous process, you have to do work on the system to make the process occur. The change in the Helmholtz energy then represents the minimum amount of work you need to put in order to get that process to occur. So it's a maximum for spontaneous processes, and it's a minimum for non-spontaneous processes. Here we have a diagram representing a situation where the change in the internal energy is negative. So this is a endothermic, this is an exothermic process. And we're also considering the case where the change in the entropy is negative. So the system is losing entropy. In order for the process to be spontaneous, the surroundings must, of course, increase in entropy, and the increase of entropy in the surroundings must be larger than the decrease of entropy in the system. So as a consequence of that, when the system undergoes this change, some of the energy of delta U must be deposited into the surroundings via heat. That's what causes the entropy of the surroundings to increase. That means that there is less energy available to do work, right? So this delta U, right, this is the change in the internal energy of the system. Because the entropy of the system is negative, more energy needs to be diverted into the surroundings as heat in order to make the process spontaneous, which means that there's less energy available to do work. For this diagram, we still have an exothermic process, but now the entropy of the system is increasing. And so we can tolerate here a slight decrease in the surroundings, so long as the change in the system's entropy is larger than that of the surroundings. That's going to correspond to heat going into the system, which means that in addition to this delta U, this change in the energy of the system, we're going to have some extra energy coming in from the surroundings. In that case, the work that can be done is going to be larger than the energy change of the system, because some of that heat can then be turned around to do work. we'll talk about the Gibbs free energy next. It's very similar to the Helmholtz energy. The difference is that there's a couple of differences, but the most obvious difference is this condition right here. The Gibbs energy is used as the criterion for spontaneity under constant temperature and constant pressure conditions. For Helmholtz, it was constant T and constant V. For the Gibbs energy, it's constant temperature and constant pressure. You could show explicitly that the criterion that dG be less than 0 is equally valid to the second law for constant pressure and constant temperature conditions. And so this is the Gibbs energy being negative is our criterion for spontaneity when temperature and pressure are constant. For finite changes, we have this equation here. It's very similar to the equation for the Helmholtz energy, right? You simply just replace G with A and H with U, and then we have the conditions that we have the equation that we had before that we were looking at. You can do a sign analysis of this equation just like we did for delta A, and I encourage you to do so. So for constant temperature, constant pressure conditions, the criterion for spontaneity is that delta G is less than 0. When delta G equals 0, that means that we have a reversible process and our system is at equilibrium with its surroundings. Delta G is usually considered to be the more important quantity in chemistry because often our chemistry experiments are carried out open to the atmosphere where pressure is indeed a constant. Here we have, let's see, do I want to do this just yet? Let's go ahead and do these problems now. So here we're considering the oxidation of glucose to carbon dioxide and water. And someone's done some calorimetry experiments to find that delta U for the reaction is minus 2808. And then delta S is known, it's 182 joules per Kelvin per mole. We're being asked how much of this change in internal energy can be extracted as heat. Notice it says at constant pressure, and then how much can be extracted as work. And so what I'll do here, first we need to set up and balance this combustion reaction. Let's see, so I think I've got the oxygen settled, I've got the hydrogen settled, the carbons are settled, and then I believe we need, I think it's 6 oxygens. So 6 plus 12 gives us 18, we've got 12 plus 6. So that's the balanced combustion reaction. The answer to part A is to calculate delta H. And so we would use for part A, we need to calculate delta H for the reaction from delta U so we would be using a formula like this. The dominant contribution to this will be the change in the number of moles of gas, and in this case we have an equal number of moles of gas on both sides of the equation, right? 6 moles of oxygen gas, 6 moles of carbon dioxide, so delta N happens to be 0 for this reaction. So in this case, delta H is approximately equal to delta U, and so the heat that can be extracted at constant pressure is simply the value of delta U. It's going to be minus 2808 kilojoules per mole of glucose that's combusted. For part B, they're asking us how much of the energy could be extracted as work, and we'll go back to the interpretation of delta A, that the maximum work is going to be equal to the value of delta A. And so that, for constant temperature conditions, is going to be delta U minus T delta S. And so we'll plug these values in, minus 2808. The temperature is 298 Kelvin. And then the value of delta S, 182.4. And what you need to watch out for, delta U is usually expressed in kilojoules per mole. Delta S is expressed in joules. So you need to correct that unit mismatch before you plug in the value. So I need to divide by 1,000 to get that in units of kilojoules. So I'm getting minus 2,862 kilojoules per mole. The reason that you can get more work than the change in delta U is due to the fact that entropy is being created in the system, and so that allows more work to be done than the change in delta U. Here in this problem, it's the same thing, but it's sort of the opposite conclusion. So we're repeating the calculation for methane. Let's see, we've got 2 4s, we need 2 there. Here, what's the maximum energy that, or the maximum, or what's the heat under constant pressure? We want to calculate delta H using this formula. In this case, we see that the change in the number of moles of gas is not equal to 0. It's going to be 1 minus 3, or minus 2. So we've got a, oh, well, I guess they've got, they've given us delta H directly, so they didn't actually need us to do that calculation. Although we should rearrange this and solve for delta U, because we need delta U to do the delta A calculation. So let's rearrange it. So I've just swapped these out, or just moved that term over. So here we've got the minus 890 kilojoules per mole. Here we've got minus -2, 8.314 times 10 to the minus 3 kilojoules per mole Kelvin. And then I'm going to multiply that by the 298K. So we'll run this through our calculator. So I'm getting minus 885 kilojoules per mole for the value of delta U. And now we want to calculate delta A. to get minus 812 kilojoules per mole. And what we'll notice is that, so this represents the maximum work that can be done for this for this process. And the reason that it's less than, the magnitude is less than delta U, is due to the fact that the entropy change for this reaction is negative. So you're not going to be able to derive, you're not going to be able to convert that complete amount of internal energy into work, because there needs to be some heating going on associated with the loss of entropy of the system. How much energy is available for sustaining muscular and nervous activity from the oxidation of 1 mole of glucose under standard state conditions? The standard entropy of reaction is 182.4 joules per Kelvin per mole. I'm not sure if I have enough information for that one. I'm going to go ahead and skip over this one because I'm not sure how to calculate it. So I'll just let this one go. And what we'll do is we'll move on to this interpretation of the Gibbs free energy. And how can we interpret the Gibbs energy in terms of work? So we've talked about in these last examples how you can use the change in Helmholtz energy to estimate what's the maximum work that can be done under isothermal conditions. The Gibbs energy also has an interpretation. It's a little bit different. The Gibbs energy represents the portion of the enthalpy that is available to do non-expansion work under conditions of constant temperature and pressure. So, right, there's different types of work that are possible. We've discussed almost exclusively so far expansion work, so pressure volume work. But you can also have electrical work and other types of work as well. And so because the expansion work is tied up in the enthalpy, when you're looking at the Gibbs energy change, it represents the maximum amount of non-PV work that you can do under conditions of constant temperature and pressure. And so that's useful if you've got, for example, a fuel cell from which you're trying to use a chemical reaction to produce electricity. The delta G value for the reaction of the fuel cell tells you how much electrical work you can generate using that fuel cell. Simultaneously, it also represents a minimum amount of work if you're talking about a non-spontaneous chemical reaction. Delta G represents the minimum amount of non-expansion work you have to do in order to get that process to occur. So delta G is a really useful quantity to know, because it represents how much work you can get from a process or how much work you need to put into a process to make it occur. Here's just a summary of everything that we've looked at so far in terms of free energy. Okay, what's listed up here are, this is how you calculate delta A and delta G. And then what's listed here on the right-hand side, it represents the interpretation in terms of work. So delta A for isothermal conditions represents the maximum amount of work that can be done. Furthermore, if you're considering an isochoric process, then it represents the maximum amount of non-PV work that you can do. For delta G, it's both isothermal and isobaric conditions. Delta G represents the maximum amount of non-PV work you can do under those conditions. I've also listed the spontaneity criterion. For when you want to use delta A, the process needs to be isothermal and isochoric. When you're talking about delta G, it needs to be isothermal and isobaric, and there can't be any non-PV work occurring. Okay, so using this as the spontaneity criterion is only possible when these conditions are met. One last thing that I wanted to point out is that, like all of our thermodynamic changes, they essentially depend upon the conditions of the experiment. So they depend on pressure, volume, temperature. And what I'm getting at here, since the maximum work that can be done and the criterion for spontaneity itself depend on pressure, volume, and temperature, that means that you can use pressure and temperature, for example, to control whether or not a given reaction is spontaneous, or to control the amount of work that you can generate. So, for example, you might want to optimize temperature and pressure so you can derive the maximum amount of work for your process. Well, the rest of the slides here just discuss the thermochemistry application of free energy, and it's fairly straightforward. We basically want to be able to calculate the change in Gibbs energy for a chemical reaction. There's two ways to go about doing it. You can either first calculate the enthalpy change and then the entropy change, and then combine them to get the change in the Gibbs energy for the reaction, or you can use what's called the Gibbs energies of formation, which you can look up in thermodynamic tables and follow that products minus reactants type of approach. And then you'll have the Gibbs energy, and so you can comment on the maximum amount of work that you can derive for isothermal, isobaric conditions, or you can use delta G to judge the spontaneity of a process under standard state conditions. Here's a brief table. There's more in the appendix showing various Gibbs energies of formation for these different substances. Here's just a quick little calculation, really just to jog your memory. You've done all of this stuff before in Chem 222. So for this particular reaction, the standard Gibbs energy change will be the Gibbs energy of formation for the product, CO2, and then you'll subtract off from that the Gibbs energies of formation for the reactants. That. And then formally you can write minus 1/2 the Gibbs energy of formation for O2 gas. However, that's actually 0 because it's an element in its reference form. And I have a little typo in this equation. I forgot the O2 part. And so what you would do is look up these quantities. It looks like I've only got the number for CO2, so you would put this number here, and then you'd need to look up the number for carbon monoxide as well. Again, that's fairly straightforward. We've already done problems that are very similar to this, so I'll let you complete it on your own as an exercise. It just uses that products minus reactants type of approach. This slide is it's meant just to point out a couple of things, and so what follows here is not something that you really need to worry about too much. I'll just point out that, again, this issue with ions, you can never study cations independently of anions in solution. They always come paired up. And so this leads to a problem with how are you going to measure the Gibbs energy change or the Gibbs energy of formation for a cation or an anion. You can't essentially, and so what we do is we arbitrarily assign the Gibbs energy of so this should be a G right here. This should be the Gibbs energy. So the Gibbs energy of formation for ions are measured relative to, and this is where the typo is, it should be the Gibbs energy of formation of H+, which is set equal to 0 by convention. And then you can do, then you can obtain these values for other ions relative to this one from doing different experiments. Here, and this is a problem that illustrates that. So you can go into lab and perform this type of experiment, at least conceptually, and in principle measure the delta G for it, how would you determine the Gibbs energy of formation for chloride? Well, what you have here is that the Gibbs energy of the reaction would be equal to the Gibbs energy of formation for the H plus the Gibbs energy of formation for the chloride, and then minus 0 for the hydrogen and minus 0 for the chlorine by definition. Well, this is set to be 0 by convention, and so the Gibbs energy of formation of the ion is just simply equal to the Gibbs energy of reaction for this particular reaction. So the answer, what is the Gibbs energy of formation of chloride? It's simply minus 131.23. And so this is what I mean by you determine the Gibbs energy of formation for ions relative to the conventional value of 0 for H plus. The Gibbs energy of formation for ions can be estimated theoretically using thermodynamic cycles and electrostatic theory. So here I just wanted to walk through this thermodynamic cycle. So look at the bottom here. So we've got aqueous H plus and aqueous chloride. And in this line up above, and this represents increasing Gibbs energy, in this line up above we have the elements. And so what we'd like to know is the reverse of this step. We'd like to know the Gibbs energy of formation of H plus and the Gibbs energy of formation of chloride. Now this we're taking to be 0, so in principle we know this because we've defined it to be 0. But then what we want to be able to do is to measure, or estimate rather, this quantity. Okay, so what we're going to do is we're going to make a thermodynamic cycle where we go around a cycle. We know that if you go from an initial state and go all the way around and come back to the initial state again, that the overall change in your state function, the Gibbs energy in this case, will be 0. So that's what we're going to do. We're going to go through a sequence of steps. And so the first step is minus the value that we want, the unknown, so to speak. The next step, notice we've gone from the aqueous ions to the elements. The next step involves dissociating the H2 molecule. Then what we're going to do is ionize that H plus atom, and then we're going to dissociate the chlorine molecule. Then we are going to capture an electron by the chlorine atom. And then now we've got the ions in the gas phase. What we're going to do is then solvate the two ions. So this line here represents the solvation of the chloride ion, and this one here represents the solvation of the hydrogen cation. And so the sum of the Gibbs energy changes for all of these different steps will add up to 0. And so some of these steps are known or estimated. For example, the dissociation enthalpy of H2 is known. The ionization energy of H plus is known. The dissociation energy of chlorine is known. The electron affinity of chlorine is known. One thing that's somewhat more challenging to calculate, although there are models for it, is the solvation of the two ions. So the gaseous ions being solvated in aqueous phase. Those can be estimated using different electrostatic models. You definitely don't need to worry about the details of this. I've just pointed it out as something that can be done. The delta G for solvation can be viewed as the work required in charging up a sphere. I should say a difference in work associated with charging up a sphere. So here we're thinking about the ion. The ions themselves as a sphere, and you're building up charge on the ions. Okay, so classically, in terms of classical, electricity and magnetism, that's a problem that can be addressed. And so what we have here, this would be the work associated with charging up a sphere the size of an atom in the vacuum, and this is the work associated with charging up a sphere in solution. So this epsilon 0, this is the permittivity of free space, and this epsilon r, this is the relative permittivity inside a solvent. And so the difference in work associated with charging up a sphere in these two medium, that is associated with the change in the Gibbs energy of solvation. And so you can use Coulomb's law and the Coulomb potential and electrostatic theory to calculate the work associated with charging up a sphere, plug in that model, and then you get this formula here that depends upon the radius of the ion. And all other quantities would be known. You could measure the epsilon for water, for example. The permittivity of free space is a constant of nature. This would be the charge on the ion. So we have here a classical electrostatic model for calculating the Gibbs energy of solvation. And it can be simplified to look something like this. And I won't work the problem explicitly, but they want you to calculate the difference in the Gibbs energy of solvation for these two different ions. And so you would evaluate this for chloride, and you would evaluate it for iodide using the given radii and the charge of -1. Take the difference, and then that would give you the answer. I think they get something like -67 kilojoules per mole difference, which is significant. You can measure that difference. And so this is just kind of a cool model for combining electrostatics and chemistry. Well, I'm going to go ahead and stop this video right here, and we'll talk more about the first and second laws and some of the mathematical details in the next video.